Alright, so these are your 12.2 notes. There's going to be some basic information that you're going to have to keep in mind. There's not so much formulas involved in this lesson like there will be coming up, but there are still pieces of information from the theorems that you have to know so that you can take a picture that has no numbers or only has one number and you can fill in a bunch of other information. So these are all things that you're going to have to memorize. Hopefully you guys have heard of the word chord before. It's a segment whose endpoints are on a circle. Diameter is a chord. It's actually the longest chord in a circle, so that is a chord. And the PQ listed right here is also a chord. Okay, so just so you know when we're referring to chords, what exactly we're referring to in the picture. Now, Theorem 12.4 has three basic concepts that you need to be familiar with. If you have a circle or if you have congruent circles, first of all, you will have congruent central angles. So if you have congruent central angles in your picture and there are chords involved with those central angles, then you can assume that they are congruent chords. That's what this first one says. Then the second one says, if you happen to have congruent chords in your pictures, then the arcs that are formed by those congruent chords are also congruent arcs. And then following that, if you have congruent arcs in your picture, then you will also have congruent central angles. So taking these three theorems, you have basically this flow chart that goes endlessly in a circle. So if you look at this, you have congruent central angles. If you have this in your picture, then you have congruent chords as well. If you have this, then you also have congruent arcs. So it's an endless circle, around and around and around. If you have one, then you have them all. So keep that in mind. So the question would be, can you conclude that you have congruent chords? Can you conclude that congruent chords have congruent central angles? And if so, how can you? Now this goes back from the first part of this class. The answer is yes. And the reason being, if you guys remember the law of syllogism, so yes, and it's by law of syllogism. If you remember, basically if you took these three and put if-thens with them, so in this example, if you have congruent angles, then you have congruent chords. If you have congruent chords, then you have congruent arcs. And if you have congruent arcs, then you have congruent angles. So if you remember when we had to make one conclusion, we could take out the middleman. So if you have congruent central angles, we can take these out. And you can go directly to the same thing. So if you have congruent central angles, then you have congruent central angles. And that's being because you have all these other things. So let me go back. Oh. So basically, if you have your congruent central angles, then you can assume congruent chords and congruent arcs by law of syllogism. Okay? Now, moving on to this stuff. This first example just uses some of those properties. So as you can see, we don't have any numbers, we just have two triangles inscribed in a circle here. So in this picture, OX bisects AOB. That's the only information, but you have that word bisects. Here's AOB. I had some questions on this. How do you know where angle O is? Well, you follow it from A to O to B, and it's where the letter O is. So it's that right there. And because the radius OX bisects it, so here's OX, that's a radius right here, you can assume that this angle and this angle are congruent because of the word bisects. So from this picture, what can you conclude? You can conclude a few things. First of all, that those two angles are the same. So you can conclude that angle AOX is congruent to angle BOX. Okay, that is 1. You could also conclude, because of our information that we got from above here, we have congruent central angles, so we have congruent chords and congruent arcs. So looking at this, our congruent central angles, so we have congruent chords here and here. So I'll put 2 so we don't get them confused with the red. So we would say chord or segment AX is congruent to segment BX, and as well as our, let's see if I can get a different color, our arcs are also congruent. So when you do your arcs, remember you do that little slanty line at the top. So these two arcs, AX and BX, are congruent. So just from this information right here, just that word bisects in the picture, you can get all 3 of these things if you remember those 3 properties. Okay, moving on to some other theorems. If you have a circle or congruent circles, then the 2 things are true. Chords that are equal distant from the center are congruent. So if you have 2 chords that are the same distance away from the center, so I can kind of draw a picture here to demonstrate what I'm referring to. Both of these are pretty much the same picture, just the converse of each other. So if I have the center and I have 2 chords that happen to be the same distance from the center, so you have that situation, then you can say that the sorry, I hit the pause button, didn't know. Then you can say that these chords are congruent, as well as, oh, I wanted to change that color. These chords are congruent, as well as the reverse if you have congruent chords. So if you're given the red information, then you can assume that these lengths right here, change the color, the length right here and right here are the same length. So converses of each other, they go back and forth. So we'll put that information into play here. Change the color again. Let's go with, I don't know, like a purple. Okay, so find AB. So if you're looking at this picture, you have 2 chords. They are the same distance away from the center. That's the key thing that you're looking for. So, and one of the chords, we have a length. We have a 7 and a 7, so the whole thing here would be 14. So if you're looking for this whole thing, then that would also be 14. So just by using those 2 pieces of information there. So moving on to the next set of information. So theorem 12.6, 12.7, and 12.8 basically all go hand in hand. Obviously we have a circle, a diameter that's perpendicular to a chord bisects the chords and its arcs. So what's going on here is if you have a circle, a diameter that is perpendicular to a chord, so here's a diameter, and if it's perpendicular to a chord, so basically if I had a chord like that, for instance, and of course we need the 90-degree angles to show that it is perpendicular, then we can say, if you have this situation, that the chord bisects the chord and its arcs. I'm sorry, the diameter bisects the chords and its arcs. So we would have these 2, yellow's not a good color. We would have these 2 arcs being the same, and the chord itself would also be cut in half. So we have that piece of information. 12.7 says if you have a circle and a diameter that bisects a chord that's not a diameter, because you have more than one diameter in a circle. So a diameter that bisects a chord that's not another diameter is perpendicular to the chord. So it's the converse, basically. So you're just moving in the opposite direction. So if you have congruent arcs or the chord is bisected, then you can assume that it's a 90-degree angle in this little area right here. Oh, let me move that off a little bit. All right, so there's that. And then the last one, get rid of this arrow now. Oh, I'm just going crazy with the arrows. Sorry, you guys, still learning how to delete stuff. 12.8, in a circle, the perpendicular bisector of a chord contains the center of a circle. So it's just giving you more of the same information. If you have a circle and the perpendicular bisector of a chord, so if you have this, where these are the same, that's a perpendicular bisector of a chord, that diameter line, then you know that it contains the center because it's a diameter, because that's what diameters do. They're perpendicular bisectors of the chords, and the diameter goes through the center. So that's all they're saying there, that you have a center and that that's a diameter. So think about these things as I explained them and try and visualize what the pictures would be. Because when you have these theorems, that's what you guys need to do. It's not just a bunch of words on the paper. You have to be able to visualize what the words are telling you they represent, and you should be able to recreate a picture that go with the words. If you can do that, then you will understand what the words are telling you. But just to, write them down and disregard them isn't going to help you. You have to be able to focus on what they're telling you. All right, the last two examples. Example 3 says P and Q are points on a circle O. The distance from O to segment PQ is 15 inches, and PQ is 16 inches. So from P to Q is 16 inches. Find the radius of the circle. So we're going to draw our circle, and we have to recreate what it's trying to tell us. We know it's circle O, so O should be in the center, because that's how we name our circles. That is always the center. The distance from O to PQ is 15. So from O to, now PQ is a chord. P and Q are points on the circle, so if we just threw them up here, here's P and here's Q. You can put them anywhere you want. If you connected PQ, the distance from the center to that chord is 15. So I know that this is 15. And PQ has a length of 16. So this is 16. Now right now this doesn't help us, but we have dealt a lot with triangles. So always try and go back to what you've been dealing with. That's the whole point. Everything builds on everything. We're not going to suddenly throw in there a trapezoid when we haven't even been working with trapezoids in this context. So make sure you're thinking when you're doing these. If I make a triangle, which happen to be the radii, these are congruent because they're radii, then we can get somewhere with that. Now, from this, if we look at it, we have the chords are equal distant from the center, so that means they are being bisected and they are perpendicular to that center point. So from that we can get our 90-degree angle, and we can also generalize that these two are the same length. So if the whole thing is 16, then both of these are 8. So now I have a little right triangle, and I can figure out what the radius is by doing Pythagorean theorem. So I have 15 squared plus 8 squared equals my radius squared. All right, now there's other ways to do this, but in this context I don't think we can figure out what it is because we don't have a central angle. You guys will get to that point where they give you more information and you can work with other formulas, but for now, Pythagorean theorem is our key. So 15 squared plus 8 squared equals the radius squared. The radius here is the hypotenuse, so it should be bigger than 15 or 8. Keep that in mind. So if you calculate this, you get 225 plus 64, square root that to get your radius, and that ends up being 17. 17 is bigger than 15 and 8, so it's a pretty decent number for your radius. Last one. Now you guys, when you're doing these, you should be trying to figure them out, like hitting pause instead of watching me do it. You should hit pause, try and figure it out, get stuck, and then listen to the explanation so that you can, let your brain process the stuff and get stuck and then get corrected so you can build these little connections in your brain, because that's what's happening. And the more connections you build, the smarter you become. If you keep letting everyone else do everything for you on here and in your notes, then you're not going to really build connections as fast as you should. So keeping that in mind, I'm just trying to help you guys out for, future, college, everything, all your classes, not just this one. All right, last example, and the bell's going to ring in a second, so I got to hurry. You have xy and yz, they're perpendicular chords within the circle that are also equidistant from the center, so that's all represented there besides the perpendicular part. Oh, there's the bell, I got to hurry. And that makes these congruent. What's the most precise name for this quadrilateral? I think you guys can all get this. It's a square because all the sides are the same, and we have 4 90-degree angles. So you have congruent chords. They're equidistant from the center, and a diameter that bisects a chord is perpendicular to the chord, so that's where the 90-degree angles come from. So from all that, we can gather that it's a square. Okay, so sorry to rush. I will, if you guys need me to post problem examples or something, if you're having a hard time with homework, if you Edmodo me and I get it, I'll be happy to make a little quick video on that problem and post it. Okay?